So now we get to the fun stuff. Well, I don't know, maybe this is fun, but we'll go to gradient descent. So let's see, minimize that, there we go. And I'll go ahead and restart this kernel. There's no spoilers. All right, so gradient descent basically is going to be using this motivation of saying, well, we don't, okay, how do I say this? One way we can solve problems is just basically find the best solution. That's what we call an analytical solution, of just like, we brute force, we figure out how this thing works and we can make it work. So equivalent to this is like if you went back to like algebra, and if I said like 3 times x is equal to, I don't know, like let's say 4. You can use the rules of algebra to analytically find the solution of what x should be. In this case, if you do algebra, you divide 3 by both sides, you get 4/3, okay? Another way you can do this is just guess. And say, I don't know, 1, right? And you put 1 there. And you're like, oh, that means that's 3, that's too small. I don't know, maybe 2. You put 2 in there. 2 is too big, 2 times 3 is 6. And you basically keep guessing back and forth, but you guess it smart. It's like, okay, well, 1's too small, 2's too big, you know, maybe like 1.5, you know, and you might kind of go from there. It's like, well, okay, 1.5's not quite right. Maybe like 1.2, and 1.3. Oh, 1.3 is pretty close. Maybe 1.35, 1.36, you know, like you can go back and forth. Basically, you keep guessing until you get to the right answer, or at least close enough, right? So that's kind of like what gradient descent is going to allow us to do. So the equivalent to this graphically is basically saying a linear regression. So we remember back to linear regression is that, oops, there we go. Okay, our linear regression, the way we actually figured out what is a good linear regression line is our RSS, our residual sum of squares, right? We would basically, we figure out what's the lowest RSS value we can get, and that would basically say, okay, cool, that is our line of best fit, okay? Now, we can actually solve this analytically. Turns out sometimes this is not really easy to do. So we can actually define something called our cost function. And I'll be honest, I don't know why it's called a cost function, to be perfectly honest. I guess you can kind of reason about it saying what is the cost of your function and matching with the actual data. I don't know. But the point is that this cost function is basically our way to measure saying, well, how close are we to the best solution, okay? And this basically leads us into our RSS for line of best fit. So I'll kind of show you how this can work out. So kind of going back, we're just going to make some random data. So I'm just putting some random seed here. I'm just literally creating random data. Hopefully you guys have kind of seen a little bit like how you can create these kind of things. I'm making a specific, you know, like line and then just randomizing a little bit of extra terms and stuff like that, because eventually we're going to use a formula to actually fit onto here. So I'm actually going to give it some, I don't know, let's give it some like random parts. There you go. Okay. So I'm going to run this guy. And so we have random data. And then right here, I'm actually going to go ahead and just plot, like say, okay, a regression formula. I'm going to give it a random guess, right? So this is what I think the line should look like. I said basically B is going to be 2, right? And A is going to be 30, which we can see here. That's not going to be true. It's slightly off, right? But then we can plot our data and we can plot our regression line and we can see how well we did. And we see it didn't work. I should probably run this guy first. There we go. And now we should work. Okay, so now we can see our little blue dots are little random points, right? And you're like, okay, cool. Like, well, our regression line, not really the best, right? So maybe we can readjust this a little bit and stuff like that. So one way we can do this is actually calculating like how far off we are with the errors and stuff like this. So I can actually define these parts here. And remember, those errors are residuals. We can find the RSS, the residual sum of squares, which is what this is right here. So I'm just gonna make these functions. And with this guy right here, I could go ahead and actually put in to say, hey, how close are we actually on this line? So if I go ahead and make this guy right here, and this is the residual sum of squares, and we're gonna have our x values, which what are x values? X, good. Pass vector was nice enough to make it something simple. And we'll put in our m, which is going to be a, well, that's confusing, but m is gonna be 30. Okay, and our intercept is going to be 2. We can see our residual sum of squares is 6,187. Okay, I don't know. Looking from here, though, you can say that's not the best thing, right? So what if we do something similar? What if we go ahead and make a new guess? So we kind of know the answer already. So I am, come on. No, why didn't you do that? Sorry, everyone. There we go. Oh, did I make a copy already? Okay. So let's make a new regression line. So let's do a regression formula. And this first, in this case, we just put X on here. But what we want to do now is go ahead and define our own B and our own A. So let's say our intercept's like, well, we'll keep the intercept at like 2. And then it should be a little bit higher up, right? Like maybe a steeper slope. So let's say I get like, I don't know, 70, right? And I run this guy. And now you can see, hey, it looks a little closer, but it looks like we might have hot-scotched over, a little too high, right? And we can see our residual sum of squares. So let's try it, with 70. And you're like, hey, that's a little bit better, 3,000, right? And I can keep doing this until eventually what I find is like, okay, I'll get like 3 and like, I'm gonna be a little bit off, like 55. Okay, and you see that's pretty close. And we can see here that our residual sum of squares is gonna be 400, right? And we could keep going further and further until finally we get the right answer, right? Actually, this might actually not be the perfect answer because it's a little bit of random data, but our lowest would be something around like 300, which is the actual base of like what this was coming from. So the point is that we could basically keep guessing, keep redrawing our line until we get better and better, and we can figure out what's better using basically RSS. So that's our cost function, saying like how close are we in drawing this line better and better to this data, okay? And this is essentially what gradient descent is doing, except instead of just guessing back and forth, what we're going to do is say, let's use some information about how this cost function changes, and we can actually determine exactly when we should stop, guessing. So one way you can kind of think about this is like, well, what if we just kept making a bunch of guesses, right? Just keep trying to change out M, keep trying to change out B, and we could keep adjusting until we get something that we're satisfied with, right? And so if we actually were to do this, we can actually, let's see here, where did my thing go? Oh, it's right here. If we were to keep doing this, here we go, we can actually make this nice little plot of our cost function, basically saying, here's our RSS, here's the different values, and here's the different M values. So as I adjust M, changing, in this case I kept, I believe I kept B the same every single time. But as I keep adjusting M, you can see here basically, well, I'm getting closer and closer. In this case, it looks like maybe around like 53 might actually be the closest value right here. This is where I get kind of the minimum value. And we can actually plot this guy. We can figure out what this function is. And basically, based on the derivative, know if we're getting closer and closer. Because as we get closer and closer to the minimum, we'll approach closer and closer to a derivative value of 0. And that's essentially what we'll have right here. So this is more or less what we're doing in a gradient function. Now, what's kind of cool is that we don't actually need to know exactly what is the perfect function every single time. In this case, I drew out like, what's it? I think like 20 different points and like connecting them all together. So there's a lot of little points in between here. But we could, for example, plot it out just, let's see here. I could have like put in the value right here and said, okay, like what is my derivative at this point? And basically, okay, this derivative is like, let's say negative, I'm making up some numbers here, negative like 50. And it's like, okay, well, we need to get higher value and stuff like this. So we can actually adjust it and move down closer to here. And we'll find out, it's like, oh, okay, this derivative right here is like negative 20. Okay, I'm making up numbers. But the point is like we get closer and closer until we eventually approach the value of 0 right here. And that's essentially how we're going to do gradient descent. And essentially we're taking little steps of figuring out what's the steepest way, what's the steepest direction for us to move towards, since we know we either go up or down. So we can hopefully find what we call our global minimum here, okay? With gradient descent, that's why we call it descent, is because we are traveling down a hill, right? And what's nice is gradient is like a super useful term, because a gradient, I don't know if you guys are familiar with like gradient and those kind of like normal terms in the sense of like, you can think of like how things like move down and stuff like that. If you talk about gradient for like, I don't know, maybe it's because I'm more like if you go hiking and stuff like that, you might talk about the gradient of a hill. Essentially that gradient is like slope. That's essentially what this is. It's like, well, we're looking for the gradient, which is actually a technical mathematical term, and we're descending down until we hit basically our minimum, which will be our most optimal value. In this case, the best value for whatever we're finding for a cost function. Okay, so let's see here if I can go and clear this out. Move this down. So you'll see gradient descent always be referred to as like traveling down a hill. And this hill, just remember, is the cost curve, the cost function. So it's basically this curve right here. Now, in linear regression, it's just RSS. The cost function could be whatever you really want it to be or whatever you're trying to optimize on. Since we know we're trying to optimize by going RSS, right, our residual sum of squares, that is our cost function. But your cost function doesn't have to be specifically RSS, okay? Now what's nice is that if you are up on the top of the hill and you're like, well, I need to get down, you can imagine, like, the way I imagine this is like you're blindfolded. So you're blindfolded and you're like up at the top of this hill and you're like, I need to go down to the lowest point, okay? What do you do? Well, what you could do is kind of like take a little step to the left, take a little step to the right and say, okay, which part is steeper? Okay, well, that's clearly going uphill. That side's going downhill. Okay, let me go ahead and go down towards the downhill part. And if it's really steep, you know, you wouldn't do this in real life, but like, it's like, oh, it's really steep. It's like, well, I need to make a big jump. So you take a huge leap forward, you know, like you jump forward because you know you're going to move a lot faster, right? Getting down. And then if you feel the gradient, like, oh, wait, you know, I don't feel it's that steep anymore. So maybe I should be a little more careful, like getting closer and closer so I don't over jump. So imagine, like, I'm trying to get a good scenario here, but it's not really realistic anymore. But if I'm over here and I take a huge leap, I might skip over this minimum point and I'll say, oh, wait, I've over jumped it. I need to go back. But if I take huge jumps every time, I'll keep leapfrogging over it. So as I get closer and basically less steep, I'll take smaller and smaller steps. And that's essentially what our gradient descent is going to do. So what's nice, though, is that this also works for multiple dimensions. So in this case, in this blue, actually, I think I changed the picture to match the one that we have in the curriculum. So let me see if I can reload that. There we go. So same one in the curriculum because they show this picture like probably like 8 times in the lesson. So you can imagine this 3-dimensional curve, right? This is still our cost curve, is in blue. And what we're doing, we're on that line right there, and we're just traveling down the line, going wherever is the steepest. Now the difference here is, like, if you imagine if you're standing right at this point right here, you're no longer just looking at up and down, you know, or left and right. You're looking left, right, up and down. So you can imagine that you have kind of like a little bit direction. I guess I should draw this out. This is probably better since I have that power. So I can imagine it's like, okay, I draw out this way, I look out this way, and look out this way, and look out this way, and say, okay, what's the steepest direction? Well, this case, like maybe there's like a slight steepness over this direction, and then down this way is clear this way. So maybe I'll kind of travel down in this direction right here. And so basically you kind of feel this part out. And this is equivalent to basically saying, okay, let me see in the X direction, in the Y direction, and then travel a direction between those two. Okay, and you can just keep doing that over and over and over again until you reach the very bottom of the hill. Okay, and that's essentially gradient descent. So that's kind of like like conceptually how this is working. Mathematically, we do something called the gradient function. Sometimes you call it grad, right? So it's this upside down triangle, or nabla, if you get anyone's uses those letters. No, but basically we're having a negative saying like we want to go in the opposite direction. So this guy right here, this nabla, this gradient we call it, right? Basically you take a function, so like some super function right here, and for example the cost curve, you take the gradient of the cost function and say, where are you the steepest? And what this will output, say you are in the steepest direction for the X direction, the steepest direction in the Y direction. If you're in 3 dimensions, steepest direction in the Z direction, and you're in 4 dimensions, Z dimension in the W direction. I don't know, whatever you want to add as the next letter. Basically it's saying, what is the steepest way up? And then you say, well, I want to go downhill. So that's why we do negative right here. And that's essentially us going down, down, down. Okay. Any questions on how this relates to you moving down the hill and stuff like that? Okay. Thumbs up if it sounds pretty good right now. Sideways, you're like, I'm still uncertain. Thumbs down, like, I'm lost. Okay, I see a little sideways, which I think is fair, because I think this part right here is the sideways for, I think, Hazel and Tara, right? Is it mostly this guy right here? Or is it like the mathematics, like the formalizing it? Or is it something else?
No, I mean, I don't know what the use case is yet, so I'm just having trouble understanding like, what we would use this for.
Yeah, okay, that's fair enough. So yeah, this cost function is an arbitrary function of whatever we want it to be, right? It's whatever we're optimizing. In this case, basically, here you can imagine the cost itself is RSS. So if I took out cost and say residual sum of squares. And so what this blue represents is like, if I have a slope of, let's say, 50 and an intercept of 15, my RSS will be something like 900. And if I have a slope up for my data, and if I have a slope of 80 and let's say intercept like 15. I know it's kind of tough for 3D me drawing, but I'll land right here, which is like, let's say a cost, an RSS of 300. And so what we're trying to do is try to get the smallest RSS, or in this case, cost, right? Cost is just basically it being in general, based on these slope and intercept. What's kind of cool is that it doesn't have to be about linear regression line. It's just that that's something that we already have available. And so essentially what we can keep doing is, instead of having to calculate every single value of the slope and every single value of the intercept and plot all those points and find the smallest value, instead what we can do, we can say, you can imagine this sheet right here is much more like, I can't do this while drawing it, but you can imagine like you start off right here with a slope of 60 and intercept of 10. And then you say, okay, what's my gradient at this point? So you can actually calculate that gradient at this exact point and say, okay, well, that means I need to move in this direction. And so you take a big step forward and you land right here and say, okay, now let me try out where I am at this intercept of 5 and slope of 70. You're like, okay, well, I need to take a bigger step in this direction, okay? And you basically keep taking a step. And what's nice about this is that you don't have to go throughout the whole thing and plot out this whole blue thing. So if I were to redraw this and I was a good drawer, this would look much more like a wireframe with me very specific points. It'd almost be like reverse Swiss cheese, if that makes sense. So I only have to look at the points that are where I land over here. So this is the way to optimize it so we don't have to look at every single value. Hopefully that kind of lands a little bit better. It's like, okay, and that's equivalent, essentially what this is equivalent of us doing is back when I was showing going from this picture right here and going up and down. If I drew a line that looks like, oops, if I were to first guess right here and you're like, oh, that wasn't very good. Okay, let me make it higher. It's like, okay, well, this is me like overshooting it. Okay, let me draw a dotted line right here and get closer and closer and closer until I approach this blue line right here. That's pretty close. Okay, and that's essentially what me going up and down, or going down the hill. I'm getting closer and closer every time. Cool. All right. All right, so that's kind of the concept of gradient descent. I still have a few more minutes. So I'm gonna show you guys a little, I kind of debated about showing this whole part because this is kind of similar to what you would do for some of the labs. This is actually, I think I borrowed this from Jeff, one of his recordings. So I know that's still in the student resources, so you're welcome to watch that through, but I'm gonna kind of go through this quickly in the sense of what this will look like. So essentially this trains CSV, and I'll show you what these parts are. So actually I'm gonna go ahead and, that's fine. Okay, this guy right here is basically, it's training data from Kaggle's housing price, stuff like this. And you can basically try to predict the price based on many different factors. So a linear regression line back in your module 1 project is pretty much this thing, right? And so I could do things, for example, like look at specific areas. So for example, if I go ahead and look at, let's say the living area by sales price, I can plot this out and I can see, okay, look at that. Like as I increase in the living area, our price goes up, okay? And I can do some, you know, like in this case, I think Jeff kind of showed like, okay, you can remove some of these outliers. You know, this is the stuff that you did back in project 1. Relook at that and then you can see, okay, look, a little bit better. So we can see the general line here. Then we can actually create our regression formula. So you can see here, that's what this guy is here. Basically our X is our data point itself. The slope is our, whatever we define it to be, basically what we think of our line, our intercept, whatever we think that is right there. We can make this guy, and then we can say, okay, let me go ahead and try to put in, for my specific slope, in this case, we start off with 0 and 0, and we try to put that in there, and you see what that plot looks like, and it's awful. You can see that black line basically doesn't look good at all, right? And we can actually calculate those errors. If we calculate this error, kind of similar to what the function I wrote, don't worry about the specifics parts, just kind of showing you the concept. We see this error, and we can actually say, okay, well, what's the value of this? Okay, well, we were really, really far off. Our error is really bad, right? So what we can do then, it's like, okay, well, what we could do is basically keep guessing, right? Change up the slope a little bit, change up the y-intercept until we maybe hopefully come across something that looks good, right? And maybe we can kind of figure out some logic of like how much we should increase by, or, you know, don't increase by a huge amount, right? But that's what we can actually use gradient descent. So this is actually gradient descent right here would look like this. And to be quite honest, usually you wouldn't, I mean, you can do this. You can do this by hand, but this right here, this M gradient and this B gradient is coming directly from just taking, how do you, what is the regression, what does the residuals look like the formula for the residuals for the slope. And you take the derivative, and this is what the curriculum will go through in the lab, is that say, okay, we get the formula for the derivative, okay, and we get the formula derivative for the intercept B, right? And basically we kind of input those parts in there, and we can actually calculate from that formula, since we know what the shape of what the cost function should look like. We just don't know what it looks like exactly. We can actually put those points in there and keep readjusting, readjusting, and readjusting. And so we can actually do this in this case we do it for blended X in this case. Basically, we're doing it for each data point. And we can basically define how to make that gradient descent. So we can imagine taking multiple steps. So our first guess, basically, we can take our first step going through. We can actually see, for example, these are different points. These are our new slope and our new y-intercept. And then we can actually plot these parts out. So if you plot this out now, we actually see, it's like, whoa, okay, we got actually a pretty, we got overshot it, right? So this is our blue data right here. So it's way, way far off. And this is where basically it's like, well, how big of a jump you do. And this is something called your learning rate. Basically how big of a step you have. And that's what this part is right here. You can see here's the B gradient times the learning rate. Learning rate is kind of like, how big of a step do you have? Do you have really big strides, or do you have little tiny strides? So this is basically too large. We're basically overstepping it by a lot. So what we can do is adjust that learning rate to something a little more reasonable. This might be a little too small, but we'll see what this looks like. So we'll go ahead and go off of this, and we'll do our next step right here. And now we can see our new error right here. And then we took a smaller step, and you can see here is that we're kind of going up. So you can see we're slightly moving from that 0, 0 point. And we can keep doing this. So basically this is our first iteration. So normally what you would do this in a for loop until you hit basically it good enough or enough iterations. But this is kind of like just doing it manually. So it's like, okay, let's do our second iteration. So our second step, basically we should do a little bit better here. We should move closer, and we can move a little bit closer to that line. You can see this is because we have a really, really small learning rate. If I instead did something like that, you'll see this just a little bit better. There you go. So you see it kind of jumped over in this case. And that's because these values are very, very big. So our learning rate needs to be relatively small, right? So you can see it kind of jumping forward. But you can see we're doing better each time. And so for our third step, we do it again based off of this one, and we can actually get a little bit better. And so what we can do is like, instead of doing 1, 2, 3, we'll basically just do it a bunch of times. And this is what we normally would do. We do a bunch of for loops, in this case, 100 times, and say, all right, keep going, basically using gradient descent, getting better and better time. In this case, I think it runs about 6 seconds. That's what I've seen before. Yeah. So you can see it took a few times to run 100 times. Basically takes every single data point and says, all right, how much should I move? Okay, and it moves that by that much. In that case, we did it for M and B. Now we can go ahead and plot this out. Oh, I should calculate the errors. So now we're actually just calculating the errors just to see what this looks like. And then we can actually show what this will plot out with the errors on, yeah. So you can see it takes a while and stuff like this. And that's because it's going calculating every single data point. So you see 12 seconds. So you can see here, basically, it's just going better and better and better and seeing like how many iterations it takes and the error. And you can see the error is actually getting very, very, very small. Basically, at a certain point, probably about like at the 40 iteration mark, we're actually getting a really, really small error, okay? And so we can actually do this whole thing. So instead of us plotting errors directly, this is how you would normally do it. It's like, okay, let me go ahead and just plot out basically do the full gradient descent using this full for loop, basically going through 100 iterations. And this right here is our error going forward. And you can see here is our line getting better and better. So you can see here, 10 iterations, we're right here, we're still pretty far off. Here's the error going from 0 to 10, going from 0 to 20, right? You can see it's getting better and better. So the one on the left is getting better and better here. And you can see our error going down, down, down. And you can see at 40, and then at 50, and then at 60, you can see it's pretty much spot on. We can keep improving it, but you can see even for every additional 10, we're not really changing that much more in the error itself. And this is like, you could technically go for 1,000 iterations, but 1,000 iterations probably gets you good enough, even though you technically are moving closer and closer, okay? And so that basically shows us how it goes to this. Now in reality, you probably won't do this yourself. You likely will use gradient descent from a package like from sklearn. But that is essentially how you would do it by hand, okay? I know I kind of went through this quickly. I think that also gives you a chance to try it out yourself with following along with the lab. But conceptually, hopefully that kind of makes sense that you're basically kind of readjusting that function. And basically gradient descent is guiding you in saying how much you should adjust it by. Okay, cool. Any questions on that then? Thumbs up, thumbs down, sideways. Pretty good. Some sideways. Okay, that's okay. And maybe I honestly, this is kind of something I feel like works a lot better as you kind of practice it through. To be quite honest, I would strongly suggest making sure you kind of have like a fresh mind going into it. Otherwise, it just feels like a bunch of numbers coming at you and just writing a bunch of code. But the main concept, hopefully, is understandable in the sense that you're just kind of keep adjusting that line, and you're really being guided by just the mathematics of saying, well, okay, let me just get closer and closer to get that zero derivative on the cost function. Okay, cool. All right, so I'll go ahead and stop it here.